Okay, I have a half-hour slot, so I will go through this presentation relatively quickly. Vinod and I created this presentation in spring, and I updated it a little bit with some of the work that has been going on since. Today, I will explain the internal details of automatic NUMA balancing to give people an overview of exactly how it works. And of course, to start that, you'll want to know a little bit about NUMA systems, and I'll jump right into that. If you have questions at any point, feel free to ask them during the presentation, and I will try to answer you. Well, what is NUMA? NUMA is an artifact of modern systems. Larger systems from SGI have had it for a while, but in modern systems, the memory controller is built into the CPU. So the moment you have multiple CPU sockets in a system, you have a little bit of memory near one CPU, a little bit of memory near another CPU, and they can each access their local memory quickly, but memory on the other side of the system is significantly slower. On a small NUMA system, it might be a 20 or 30% performance penalty to access memory that is on the other socket. On a very large system, it might be a factor 2 or 3 performance penalty to access memory that is far away. And there are two kinds of new words that NUMA introduces. You're probably familiar with them. A node is simply a collection of physical CPU and the memory that comes with that CPU. And an interconnect are the straws that the data travels through to get from one node to another. The 4-node HP systems and many other 4-node systems look like this. We have 4 nodes, each of the corners. We have a processor. They are all attached to their own memory. They may or may not have their own I/O channels. And all of these are directly connected. And the light blue arrows here in the middle are the interconnects between the different nodes. And when a processor on one node needs a piece of memory that is on another node, it will have to send a message over the interconnect to ask for the memory elsewhere in the system. And that's that is what slows down the access of remote memory. You can make these NUMA systems as large and as complicated as you want, which our friends at HP have done. A DL980 has 3 levels of distance between the nodes. Every one of these blue boxes here is a NUMA node, a processor with attached memory. One of these is directly connected to another one of those. But if this processor here wants to access the memory over there, it has to send a message through the node controller, which has to send a message to the next node controller, which then has to send a message there, and hopefully it can get the memory from there. If you're out of luck, the memory might be dirty in the cache over here, and it's going to take even longer to get. So the larger the system gets, you can see the more overhead is involved in accessing memory that is not local to the CPU, but remote on a different node. And HP has made a large system as well, which again has 2 nodes close to each other, connected to the rest of the system through an interconnect. This is a really big, fast interconnect. So all the nodes elsewhere on the system are roughly the same speed. Now, the performance of NUMA systems is determined by a few different considerations. Firstly, going through the interconnect makes memory access slower. But if everybody tries to go through the interconnect at the same time, the interconnect will get congested and things get even slower. The second consideration is the fact that processor threads and cores do share resources. So if you have one big program running on a NUMA system, it may still be better to spread out the different tasks in that workload to the different nodes, because then you get more CPU cache available. Some of the threads might be running in turbo mode if you use a few threads everywhere and leave other threads idle. So you do not want to just jam everything onto one socket and leave the rest of the system unused. To deal with that, the automatic NUMA balancing code has two main strategies. Andrea Arcangeli came up with the realization that both of these are needed a few years ago. The first one is called CPU follows memory, which means we measure where a task has its memory, and we try to run the task where it has most of its memory. And the second one, memory follows CPU. We try to run a task where most of the task's memory is, and the rest of the memory we can migrate over. We simply copy the data and make the program use the memory in the new location. Sounds pretty simple so far, but there are lots of little details and corner cases involved, which I will slowly walk you through. It all starts with the page faults, and we'll slowly get into more and more complicated details of the NUMA code. Periodically, we simply go through the memory of each process that is running on the system, and the program will unmap a little bit of its own memory over time. It does that while running in kernel space. And we do that by simply clearing all the permission bits in the page table. So you have a page table entry still points at a piece of memory, but the program is not allowed to read it or write it or do anything else with it. And when it tries to access it, CPU generates a page fault, and the page fault handler sees, oh, this is a NUMA page. So I will give it back to the program, and I will do something else with it if necessary. One of the things that we will do at NUMA page fault time is migration. If the same program or the same NUMA node access the same page multiple times in a row, then we migrate the page. We simply copy over the page data to the location where the task is running, and then we point the page table at a new location, and the memory that was remote is now local to the program, and it can run a little bit faster. But page migration is pretty expensive, so we do it when we're pretty sure about it, and we also want to make sure that the program is relatively stable in that location, because if the program keeps moving around and we have to keep copying the memory all over the system, then the NUMA code will slow things down more than it speeds things up. So the second element is figuring out where each task's memory is. To do that, we keep a set of statistics per task. And every time we get a NUMA page fault, we will simply increment the counter. On this task, had a page fault on node 0. If the memory was on node 2, this page accessed memory on node 2. And we keep that as a floating average. So over time, we have a pretty good idea where the memory is that the different tasks are using. And we get a bit of a classification of the faults going on as well to tweak other things in the policy. We track whether a fault is local or remote. If it is on the same node where the task is running, it's local. If a program has almost all local faults, that means that we don't have to do anything else with the NUMA code because it's already running in an optimal way, and then at that point we can slow down the scanning. If a task has too much of its memory running remotely, then we should probably scan more often, figure out what is going on, and correct the placement of the task. And the same thing is private versus shared. If you are dealing with a multi-threaded program, like a KVM guest, you will have multiple threads accessing the same memory, and placement gets a little more complicated. And I'll slowly get into that further into the talk. First, we have a simple example of fault statistics. We have two tasks, A and B, and a system with 4 NUMA nodes. Task B has almost all of its accesses on node 0. Well, task A has most of its accesses on node 2. That's pretty obvious. If we run task B on node 0 and task A on node 2, most of the memory access are local, and we can migrate the rest of the memory over, and it will all run fine. It's pretty obvious, but it's not always that easy. The main cause is when tasks are sharing memory. You have multiple threads in a KVM guest, for example, the QEMU process itself, or a JVM, or you might have a database with a shared memory segment. And sometimes these tasks also have more threads than we can run on a particular node. If you have 2 CPUs in your system, and each of those has 4 cores, but you run a program that needs 8 CPU cores, then some of the threads will be running on one side of the system and some on the other, and we have to figure out which is the best where and spreading the memory between the nodes. And this also leads to some other constraints. The NUMA code is not the only placement code in the scheduler. There's also load balancing code, which looks at all the different parts of the system, and if there's an imbalance in load, the load balancer tries to even things out. So you have about the same activity everywhere in the system. And if the NUMA code always does what it wants to do, then the NUMA code might create an imbalance by moving a program, and then the load balancer might move some other program back over, and things keep tumbling around the system like a washing machine, and we keep creating more and more overhead. So the NUMA code has to be very careful to only move things around when it does not create an imbalance that a load balancer would trigger. And at least the 2 things that the NUMA code can do. If the load between 2 nodes is pretty similar, we can move a task from one node to the other, and it will still be pretty similar. Load balancer is not going to do anything. We are free to do that. The second thing that we can do, if we have a task running on one node and a task on another node, we can always swap them around, move them to each other's location. The load balancer will still be happy. And both of these things are examined in the task placement code. The algorithm simply looks at all the nodes on the system, and if a node looks like it is a better location than the current node where the program is running, then it will check all the CPUs on that node. If the CPU is idle, and we can move the task without creating a load imbalance, we'll probably try that. If the CPU is not idle, we look at the task that is currently running on that CPU, and we look whether a task swap would be a good option. And we find the option that has the best score and do that one. I've got some very simple example to start out with. We have 2 programs running on the system, task A and task T. They're both on node 0. On the right-hand side, we can see that task A has most of its memory accesses on node 1, and task T, most of its memory accesses on node 0. If we simply move task A to node 1, we remove an imbalance in the system, so we make the load balancer happier than it is now, and we improve the NUMA locality of task A by 40%. It's pretty easy. We move task A over to node 1, and things are better than before. Let's make it a little bit more complicated. We have task A, like before, most of its memory access is on node 1, but it's running on node 0. But this time task T is running on node 1, and task T has most of its accesses on node 0. It's again a fairly easy case. We swap the 2 around, and locality improves for both of these. So let's make it a little bit more complicated. Task A is the same as before. Moving task A to node 1 is a 40% improvement in locality. But this time around, moving task T to node 0 would be a 20% reduction in locality. Now we cannot just move task A over to node 1 and leave it at that, because that would create an imbalance, and the load balancer will do something about that. And we don't know what task it is going to move back. So what we have to do in this case, we simply swap them around, and we get a net 20% improvement. And the memory migration code will fix up the rest later. Now let's make it a little bit more complicated still. We have a situation, task A exactly the same as before, but task T, running on node 1, has 80% of its accesses there, and only 20% on node 0. In this case, the improvements that we get from moving task A to node 1 is smaller than the reduction in locality that we get from moving task T over to node 0. So it's best to just leave things alone and let the memory migration code deal with it and gradually move the memory over to where the tasks are. Well, you've noticed the theme here. Things get more and more complicated throughout the talk. Multiple tasks can access the same memory. Looking at a large multi-threaded process or a database, we have some magic in the page fault tracking code. We store the CPU number and the low bits of the page ID, or the process ID, sorry, in the struct page. And in the next fault, we can see whether the task that is faulting the page now has any relationship to the task that faulted the page last. It might be the same task, in which case we simply move the page to where the task is. Or if they're accessing the same page and they're writing to it, we know that these two tasks are related, and we group them together in a NUMA group. And we can add more and more tasks to the NUMA group over time. And, well, some files everybody accesses, but they do that read-only, things like the C library. We ignore those because if read-only faults were counted, every process in the system would be in the same group. And yes, that was a bug we had early on. Well, the group statistics look exactly like the task statistics. The statistics of a NUMA group is simply the sum of the statistics of all the tasks that are part of the group. And when we are comparing two groups, two tasks from different groups, we look at the group statistics. If we are comparing two tasks from the same group, we look at the task statistics. In this example here, you can see we have two processes with 2 threads each, and they're all jumbled over the system. We have the green workload and the blue workload, and they look pretty equal right now, but one of them is going to win. Say that the green task wins on one of the nodes, and at that point, the green task gets pulled over. If the green task has slightly more accesses than the blue task on node 0, and the blue task has more on node 1 or is more even, we end up moving the tasks around first, and after that, the rest of the memory will get migrated over to wherever the tasks are for this group. But we do want this to be somewhat even. If you have a very large workload, it is possible that the same program takes up space on multiple NUMA nodes. And in that case, we want to limit the number of memory migration that is going on, because we would just keep bouncing it around if it is accessed from different nodes all the time. And memory that is private to each of the threads We want to locate locally where the thread is. And we want to maximize how much memory bandwidth the application has. If an application has all of its memory on one node, but half of the threads are running somewhere else, it's going to run slower, because everything has to go across the interconnect into the one memory bus. We want to spread the memory somewhat evenly between nodes. If you have this situation where a single workload runs on 2 NUMA nodes, and the memory is not divided evenly between the nodes. At this point, the program does not run as fast as it could. We want to fix this. To do that, we look at all the statistics that we have. We figure out which nodes the program is using really actively. Private faults are always allowed to migrate. If it is only that thread using the memory, it should have it locally, and we don't care about the rest. But shared faults are only allowed to migrate from a more heavily used to a less heavily used node. So it looks like this. From left to right, shared fault migrations are allowed. From right to left, they're blocked because the left node already has much more memory than the right node. And eventually, it will look like this, where both are about the same, and there is no point in doing migrations of any memory that is shared between different threads in the NUMA group. Only private faults still get migrations after this state has been reached. And this gives us a good use of memory bandwidth for a very large process, and a minimum amount of overhead because we stop most of the page migrations. We never do those. Now we have a part of the talk that I'm going to have to skip because we only have 5 minutes left. The slides are online for both of the conferences. And for, there we go. So I'll just go into more technical details of things that I'm working on and things that we're not working on yet because we haven't gotten around to it, but stuff that a code should probably do in the future. A big one is dealing with very large NUMA systems where if we are dealing with a workload that spans multiple NUMA nodes, the big HP system that I showed, the diagram of earlier, if we have 4 workloads on that system that each use 2 NUMA nodes, we want those 2 nodes for each of those programs to be nodes that are sitting right next to each other, and not nodes that are all the way on the other side of the system. And I have an implementation for that. I actually posted it to LKML last week, and Vinod verified it. It seems to work. Trying to get that code upstream. If we look again at the DL980 system again, if we have 4 workloads running that each take 2 nodes, you want a workload to simply take 2 nodes, use up 2 nodes that are directly connected to the other. And you do not want workloads to be spread around, say, between node 7 and node 3, because then all the communication between threads of that workload have to take 2 extra hops through the Backplane controllers. And what we do in this case is do a comparison between groups of nodes. In a Backplane system, like the DL980 from HP or their new systems, you have natural groups of nodes. And if we are comparing, if we have a task running, a group of tasks running on node 7 and on node 3, and we have another group of tasks running on node 6 and node 2, we want to untangle them and make sure that all of the processes of one task are over here, and all of the processes of the other group, other NUMA group, are over here. And we can do that by simply noticing, well, hey, if we are comparing tasks on node 7 with node 2, for example, we notice these nodes are 3 hops away from each other. We have to traverse 3 links to get to the other side. And at that point, we can add up the score on each of the nodes on each side. So we add up the scores from these 4 nodes. We add up the scores from those 4 nodes. At that point, the different NUMA groups will win from each other on a particular side of the system. If we do a comparison between node 5 and node 7, for example, we see they're 2 hops away. And at that point, the groups are smaller. We add up node 6 and 7, and we add up node 5, 4, and 5. And we will naturally untangle workloads that way, so they end up running on nodes that are the closest to each other. We need a slightly different algorithm for systems that do not have a backplane. It is possible to directly connect Intel and probably AMD CPUs as well to each other using the CPU QPI links. In this situation, we have 2 rings of nodes, and they are connected to each other in a funny way that makes it possible that each of these nodes is directly connected to 3 others, and the other 4 nodes in the system are only 2 hops away. The big difference with the topology of the HP system is that on the HP system, the hops in between are node controllers. They cannot run programs. On this system, going from node 3 to node 8, the hop that is in between is also a NUMA node, and it can also run programs. And this changes the algorithm a little. And specifically, we simply add up the faults from nearby nodes divided by the number of hops or divided by the NUMA distance from these nodes. And a node that is close to a node with a very high number of NUMA faults will get some of those faults added to it. And this means that if a program, for example, is currently running on node 1 and node 6, I'll see nodes 8 and 7 and 5 and 2 will all get a little bit of extra score because they are close to one of these. CPU 3 will get a very high score because it gets half of these guys' faults and half of this node's faults. And by giving this one a high score, whichever one of these is the lowest score will probably end up migrating the tasks here. And then suddenly, the group of tasks is running on 2 nodes that is sitting right next to each other. Well, that's how we solve this part of the problem. I think it's 3 o'clock now.
We have a half-hour break. Though,
I have about 3 slides left, or 4 slides, so I'll take a few minutes from your break. There's another thing where I'm not sure what to do yet. Tasks that are running on the NUMA system may have memory that is not movable. It could be part of a KVM guest that is used for direct for device assignment. Or it could be a piece of mlox memory or anything like that. The memory is not movable, but we might still want to get page faults from it. Because getting the statistics of the memory...
Why is mlock memory not movable?
Right now it's an implementation thing, but it's mostly there because we don't know why something was mlocked. And we have no way to distinguish whether it was an mlock because people are doing direct accesses to it or simply because they don't want it swapped. There's some work going on to split that out, but right now we don't really know. But the memory that is not movable is still used by tasks that can be moved. And having the faults from these memory areas in the statistics, it may help us do better placement of the tasks using this memory. But it also generates extra overhead, getting page faults on memory that we cannot migrate. And whether or not this is worth doing is something that we'll just have to experiment with. KSM is another issue. It's mostly used for KVM guests. When system memory is getting low, it finds pages with identical content. It merges them in one memory page. KSM right now has extremely simple NUMA support, where it will only merge pages between tasks on the same NUMA node. But afterwards, the task could be moved to a different NUMA node, and the KSM page is no longer local. We may want to do something with that. On the other hand, people who use KSM, they want to cram as many virtual machines on the same system as possible. So they may not even be interested in having multiple copies of the same page. They would rather have their guest run 10% slower than use up 2% more memory and have fewer guests on the system, or have swapping, which slows things down even worse. So I'm really not sure if this is something that we should touch. This is a big one, interrupt locality. If you have a 40 gigabit network card on one NUMA node of the system, and your KVM guest is running on a NUMA node 2 hops away, you are not going to do 40 gigabits. So trying to get the KVM guest to run where it is doing I/O is a big thing. Right now, this is something that needs to be done manually. It is something that we would like to do automatically, but it's really difficult just to figure out how to implement this. When should the IRQ affinity outweigh the memory affinity, for example? If we have 2 guests using the same 40 gigabit interface, which one is more important? Is it the one that is doing more network traffic? Or is the only reason that it does more memory traffic the fact that it runs closer by? So it's not really easy to figure out any answers to this. And I would like to fix this someday, but to be honest, I'm not quite sure where to start. Inter-process communication is another area where different tasks sometimes do a lot of communication with each other, usually across loopback network sockets or pipes, things like that. Again, we can measure how much different tasks talk to each other. There's already some code in the scheduler to try and move tasks closer to each other when they communicate with each other. But that code is totally independent of the NUMA code today. And even if we implement it with the NUMA code, at what point does inter-process communication outweigh memory and CPU locality? It gets more complicated once you're dealing with multi-threaded programs. It's one of those areas where I've got some vague ideas in my mind on what statistics we could gather to look at, but I'm not entirely sure yet how to use them. But the NUMA balancing code has been getting better over time. It's covering more and more workloads. For some simple workloads, even for KVM guest placement, we can get within a few % of optimal memory tuning for certain benchmarks. For things that have more complicated requirements, like doing lots of inter-process communication or networking, and other things that this code simply does not measure, you may still need to do manual placements, because at the moment we only do memory and CPU placement. But the code is slowly getting better, and the range of systems where automatic placement works very well is growing over time. And for some cases as well, we have seen that when workloads go idle and then they get busy again, in those cases, automatic placement can work better than manual placement, because manually you don't really know what workload will be busy when and when it will be idle. And having the automatic placement code deal with some of those things can work better than manual already. Any questions?
With VMs, I think that threads are also interesting. Do you only deal with processes or also with threads?
We noticed that threads, they access the same memory and they get grouped together. We use the same grouping mechanism for processes that have shared memory and for threads that share all memory.
What about shared memory that many processes uses and on large systems that have lots of large instances? How much does that affect performance? I mean, for example, if libc is in one node and all the tasks running on the other node are using it, or even an even larger library?
Well, for things like libc, it's probably not a big issue. It is always read-only, which means you can always cache it easily. But things that are...
That does not fit on the cache.
Yeah. Things that do not fit on the cache and things that are... it really depends on the topology of the system. Let's go to this one. If a task has memory here, but it is running here or there on CPU 1, it has a direct link, then the slowdown in accessing that memory might be 20 or 30%. But a 20 or 30% slowdown in accessing the memory is not the same as a 20 or 30% slowdown in how fast it runs, because we'll have some of the memory locally as well, and it will also be spending some time simply doing stuff on the CPU and not waiting for memory.
So you don't know any workload that could be really affected by loss of shared memory?
Oh, they definitely are. On systems like this, vnode has, he's sitting over there, by the way, has some measurements where if a program runs on two nodes right next to each other, it could run about 20% faster than if it's running over here and over there. The amount of distance between them, it really matters.
If too many tasks are using it, have you ever considered making a reverse ASM? I mean, will it work to duplicate the shared memory if it's read-only?
People have looked at that in the past, and it had made a big difference on really large NUMA systems. I don't know if it is worth doing today, because CPUs have really large level 3 caches today. And the code that is used a lot by different processes in the system can pretty easily be cached.
Yeah, you mentioned earlier that you have a split between a load balancer and a NUMA code. And it does sound a bit like you have two systems fighting over optimum placement there. How much do you think improvement would it be to just switch off the load balancing code and say just do NUMA placement and do one or the other? Are there any numbers there available?
I think we still need the load balancing code, because if we have a system like this and all the programs are running here, then it will be a lot slower than if the programs are spread out across the rest of the system.
Can you maybe make the load balancer aware of NUMA? Put it in its metrics?
The load balancer is already aware of NUMA, and when deciding what process to move, it will look for a process that is not running on one of its favorite NUMA nodes. It will initially look for that.
So it's not really a competition, there is some kind of consideration.
Yeah, the two pieces of code try to be considerate of each other.
Yes, this reminds us slightly of back in the old days we had something called cache-only memory architecture, COMA, which was kind of the ultimate where you didn't have memory, you only had cache, which was, I suppose, would be fairly useful for this if you have, but I think in general, if you have a lot of shared memory, then most of it would have to be read-only. Otherwise, it's a bad design.
It depends on what you do, what a shared memory is for. If it's a lot of very actively read data, having it read-only is extremely useful. But if you have, say, a database, then using the shared memory, even read-write, is still a good idea because it is so much faster than going to disk.
Yeah, that's true. But another question was this, the tool, you had some slides you skipped. Yes. On the tool side, because it seems like this really begs for better tools.
There are a good number of NUMA tools out there, and yeah, I encourage you to download the slides and play around with the different tools that are listed in the tools section.
Rik, do you have any tips for application programmers to write applications in a way that can help you?
That is a good question. I guess one of the things that I have seen I have an example of what not to do. We ran into that a while ago. The customer, by the way, is also aware that they should not have been doing this, but it's an artifact of the tool set that they were using for programming. They have a particular tool set, something in Java, where a different thread handles a different step in the process of dealing with a request. So a request would come in, get processed by one thread, handed off to the next thread for the next step in processing. And there were 20 plus different steps involved. So each single request that came in got handled by 20 different threads that were spread out all over the system. And the way to do that kind of thing instead, when you get a request, you would route it to one particular instance of a thread so it could handle that request locally and then send back the result.
So once two tasks get put into the same NUMA group, are they never split apart? They stay that way forever?
If two tasks get put in the same NUMA group, there's really only one way, or there's two ways of leaving the NUMA group. One is exiting, that's the obvious one, but the NUMA group can also merge into another NUMA group. If you have a task with 5 threads, for example, and they slowly discover that they are sharing memory, you might have a NUMA group with 2 tasks in it, another NUMA group with 3 tasks. And if one of the threads in a NUMA group with 2 tasks discovers, then, hey, I am sharing memory with somebody in a larger NUMA group, then it will move into the other group, and eventually the other guy will move too.
Can you disable NUMA balancing?
Yeah.
Can you disable NUMA balancing and then re-enable it and clear all the stacks?
Disabling NUMA balancing and then re-enabling it does not clear the stats, but the stats age out over time. So they disappear fairly quickly.
What I'm thinking of here is the case where you've got a big multi-thread application that has a initialization phase which is really bad and shares everything, but then settles into a long-term pattern where there's reasonable locality for each thread. Is it going to be too late by that stage and it will have glued all the threads together so it won't be able to...
A VM can do that. I mean, a VM running NUMA balancer inside it can start doing stuff all to...
Well, having different threads glued together in the same NUMA group, but afterwards accessing their own memory, is totally harmless because we will move the private memory for each thread over to where each of the threads is. And if you have a number of threads accessing the same memory inside a group, chances are those threads will still get grouped together on the same NUMA nodes. And the threads accessing other memory will get grouped in other NUMA nodes.
I think it means if they start sharing lots of memory accessing each other and then they stop sharing, they start working.
Yes, and that's fine because we detect that the same memory is used several times over by the same thread, and we move it to where the thread is.
All right, your extra time's up.
Yep. It is time, to get something to drink and move on to the next store. Thank you.